In this video, we're going to look how UnicornOne enables AI machine learning integration. Rather than forcing users into a single AI architecture, UnicornOne provides three different integration paths depending on how deeply the users want to integrate their models. And this is the important distinction. It is relatively easy to connect AI models to an individual instrument or build a custom application around a specific experiment. The much harder problem is creating a laboratory-wide software environment where hardware, data, users, and AI can work together without rebuilding the infrastructure for every new application. This is the problem UnicornOne is designed to solve. Before we look at each integration option in turn, let's first explore what UnicornOne is. UnicornOne is an AI native laboratory operating system, or LabOS, designed to unify laboratory hardware, data, and software through a common control plane. UnicornOne is to the laboratory what Windows is to the PC, a vendor-agnostic operating system that provides a universal platform for user customization and innovation. Traditional laboratory software is normally built around individual pieces of equipment. A custom LabVIEW application, Python application, or vendor control package can be extremely effective at controlling the system it was designed for. But as the laboratory grows, those applications become islands. Every new instrument introduced another hardware interface, another data format, and another integration problem. UnicornOne takes a fundamentally different approach. At the hardware level, the UnicornOne hardware abstraction layer, or HAL, provides a consistent interface to the laboratory equipment. At the data level, system information is continuously abstracted, structured, analyzed, and stored, allowing process data, metrology data, system state, and analytical results to be accessed through common interfaces. This abstraction is what changes the problem. An AI model no longer needs custom code to understand every pressure gauge, shutter controller, read system, or temperature controller in the laboratory. UnicornOne handles that complexity. The AI interacts with the laboratory through a common software environment rather than a collection of individual machines. The question then becomes, how does an AI model actually interact with UnicornOne? And this brings us back to the three primary approaches. The first is through IronPython Recipes running directly inside UnicornOne. The second is through the built-in HTTP server and REST API, allowing external applications to communicate with UnicornOne. And the third is through an AI/ML workbook, which allow users to build complete visual applications that integrate directly into UnicornOne interface. The first option is UnicornOne's built-in recipe environment. UnicornOne implements CLR-based IronPython scripting, giving users a powerful way to create programmable recipes directly inside the application. These recipes can perform the normal tasks associated with epitaxial growth, controlling shutters, temperatures, pressures, fluxes, and layer sequences, but they can also do considerably more. Because IronPython can create HTTP clients, a recipe can communicate directly with external AI and machine learning services, allowing AI models to participate directly in the experimental workflow. To facilitate this, UnicornOne's Recipe API has access to structured process data, live system values, instantaneous read analysis, flux data, recipe state, and other contextual information. The recipe can therefore gather the current experimental state, send it to an AI or machine learning model, receive a result, and then immediately use that result in the running process. Here we have a conventional epitaxial growth recipe. The recipe uses the standard UnicornOne Recipe API to perform familiar operations such as ramping temperatures, opening and closing shutters, and waiting for process conditions, and controlling the growth sequence. On the right, UnicornOne automatically interprets the recipe and constructs the corresponding layer sequence. This is possible because UnicornOne doesn't just execute commands. It understands the underlying process through its data abstraction and analysis framework. Now let's open a different recipe. At first glance, this looks completely different. Instead of containing the experimental logic, this recipe simply creates a HTTP client, packages the relevant process information, and sends it to an external application. The external application could implement deterministic algorithms, conventional software, or a machine learning model. UnicornOne remains responsible for hardware abstraction, data and process execution, while the external application provides the decision-making logic. And critically, changing the intelligence does not require rebuilding the laboratory control system beneath it. The second integration option moves the AI logic completely outside UnicornOne. UnicornOne includes a comprehensive HTTP server implementing a RESTful interface. The same structural information available internally through the recipe API can also be exposed externally through the REST API. This means the same process values, system states, analytical results, and other structured laboratory data. Responses can be provided as HTML for human inspection or as structured JSON for software AI and machine learning applications. This creates a completely external application layer. Users can build their own Python applications, machine learning pipelines, or autonomous control systems using whichever libraries and frameworks they prefer. In this architecture, UnicornOne effectively becomes the laboratory execution layer. The external application can request data, analyze the current state of the experiment, and then send commands back through the REST API. This is very different from writing a Python or LabVIEW application that directly controls a collection of hardware. The application does not need to know serial protocols, which vendor manufactured the instrument, or how the underlying data is stored. Those problems have already been solved by UnicornOne. The developer can concentrate on the new application, algorithm, or AI model rather than rebuilding device integration and infrastructure. It also means the AI application no longer needs to run inside UnicornOne at all. It could run on the same computer, on a dedicated GPU workstation, on a local server, or in the cloud. Now let's look at the REST API. Here we're opening UnicornOne's built-in AI landing page in a standard web browser. Each endpoint exposes structured laboratory data or control functions that can be accessed by external applications. Responses can be returned as HTML for human inspection or as a structured JSON for software and AI models. Now we'll switch over to Visual Code. This simple Python 3 application using the standard request library to query 3 live values from UnicornOne over HTTP. When we run the script, UnicornOne responds with the current values in real time. The important point is not that Python can read the 3 values. Almost any control system could be made to do that. The important point is that the same interface can expose structured information across the entire laboratory without the external application needing to understand the hardware underneath it. That is what makes UnicornOne a platform rather than another control application. The previous two approaches are extremely powerful, but they are largely headless, meaning it can be difficult for a human operator to visualize the state of the AI application and track its progress. They provide the communication control layer, but not necessarily a rich graphical interface for the AI application itself. This is where AI/ML workbooks come in. Workbooks allow users to create their own plug-in DLLs containing both application logic and a complete graphical user interface. These are fully user-owned C# libraries that integrate with UnicornOne through the UnicornOne abstraction DLL. A workbook, therefore, has access to the same structured information available through the Recipe API and REST API, including process values, system state, analytical results, and other structured laboratory data, while presenting its own interface as a native part of the UnicornOne environment. This allows developers to create complete AI and machine learning applications containing elements such as live RHEED videos, Microsoft charts, real-time status messages, control widgets, and dedicated results panels. Just like the REST API, developers are extending the UnicornOne platform rather than modify or rebuilding the core control system. The AI logic itself can still run wherever makes the most sense, directly inside the plugin, in a local Python process, on an edge system, or through a remote cloud service. The workbook simply provides the integration and presentation layer. This means users are not limited to just adding headless AI models in UnicornOne. They can create entirely new scientific tools and applications that behave as though they were built into UnicornOne from the beginning. Let's look at a workbook in practice. We simply select from the list of available workbooks. Here, the gallium nitride live workbook provides AI-assisted temperature calibration and growth mode analysis for gallium nitride or sapphire. It combines live RHEED input, analytical results, charts, and task controls inside a single native UnicornOne interface. The user can run the complete workbook end-to-end or execute individual tasks. For example, determining the offset between the thermocouple and the actual substrate temperature. You simply select it and the task starts.
Intensity not stable.
From here, UnicornOne handles the data access, equipment interaction, and workflow execution, while the workbook provides the application-specific intelligence and interface. These three integration methods, IronPython, REST, and Workbooks, can also be mixed and matched depending on the application. For example, an IronPython recipe could launch and interact with a workbook, or a recipe could be created and executed remotely through the REST API, with the orchestration layer running completely outside UnicornOne. Because each method operates against the same underlying abstraction, developers can change or extend the application layer without rebuilding the hardware integration underneath it. This is an important difference from traditional bespoke control software, which often becomes increasingly difficult to maintain as new functionality is added. UnicornOne is deliberately designed around the opposite model, a stable operating platform extended through defined interfaces. The underlying architecture remains the same. UnicornOne provides the hardware abstraction, structured data, and process control, while users remain free to choose how and where their AI runs. As laboratories adopt AI, the challenge is no longer building individual models. The challenge is connecting those models to real laboratory equipment safely, consistently, and at scale without friction. That requires more than another bespoke control application. It requires a laboratory operating system. Whether you run AI inside a recipe, inside a workbook, on an edge computer, or in the cloud, UnicornOne provides the hardware abstraction, structured data, and process orchestration that makes it possible. Put simply, UnicornOne doesn't just add AI to your laboratory, it makes your laboratory ready for AI. To learn more about UnicornOne, contact our team or visit our website.